where is the location of the holes in the function? And so we have the function f of x. What I want you to recognize is that holes are also known as removable discontinuities. So that's important to write into your notes, that if they ask for you to identify removable discontinuities, and as you move into calculus, that is equivalent for us being able to identify the holes of the graph. So we're going to talk about the steps, and we're going to practice a few problems after this just to feel more comfortable with it. The first thing we need to do is we need to factor the numerator and the denominator. Now the great thing about this problem is it's already done for us. Then we need to identify, is there any common factors? Now before I do that, I like to take this and I like to write it in expanded form. So I'm going to write f of x equals x minus 5 3 times, and x minus 7, x plus 1 twice. And I know there's not much room here if I move this off to the side for you to see. So I've factored the function, it's done for me, and then I've gone ahead, I've expanded it out, and now I'm going to look for common factors. So I'm looking at the top and the bottom, and it's like a 1 for 1. What would cancel out? You can think of it as that way. So I see an x minus 5 on the bottom and x minus 5 on top. Okay, that's one factor. I see an x minus 7 on the top and an x minus 7 on the bottom. All right, so the next thing we're going to do is we're going to set each of these equal to 0, and we're going to solve. So I'm going to take the factor x minus 5, I'm going to set it equal to 0 and solve, and the factor x minus 7, set it equal to 0 and solve. Now I want to stop for a second and make sure that I did write this problem down correctly. That does look like it is correct. Okay, so over here I'm going to add 5, so x equals 5 could be a whole, also known as removable discontinuity, plus 7. So here's what I know right now. I know that there potentially is a whole at x equals 5, and there potentially is a whole at x equals 7. So I've done steps 1, 2, and 3. Now step 4 is we want to know what is the y coordinate. And so when we want to figure out the y coordinate, we're going to come up above and I'm going to write down what is my simplified expression. So notice that in the simplified expression I have two groups of x minus 5. So I think I can do that right off the side here. So this is the simplified expression. There's two groups of x minus 5 and there's two groups of x plus 1. In the simplified expression, we're left with x minus 7 on the bottom. Okay, this is the simplified expression. Now, when we have a hole in the graph, you're thinking, what does that look like? So I can just give you a quick example here. If this would be an x, y axis, a Cartesian plane, and if I was just going to give you an example of a function that has a hole in the graph, it may look like this. And so as an example, we would say at 2, 1, there's a removable discontinuity or a hole in the graph when x equals 2. Now where exactly is the hole? It's at the placement of 2, 1. So we could say as the limit approaches 2 from the left and right, it's going to approach the value of 1. It's going to approach the value of 1. But there's not an actual point in the graph. There's not an actual output because there's a hole there. Okay, so let's come back to what we have right now. We believe, without doing any more examining, we believe that x equals 5 and x equals 7, before examining more, could be potential holes. How do we figure out what is the y coordinate? We come over here to our simplified expression. So I've simplified it, two groups, put everything down, and now I'm going to substitute in 5. Let's see if we actually get an output value to this. So I'm going to grab my calculator, and we could do this by hand as well, right? But I'm going to substitute in 5 wherever I see an x. So 5 minus 5 squared, and 5 plus 1 squared. Now some of you may have already recognized what this is going to be, because if 5 minus 5 is 0, and 0 squared we know is 0, 0 times whatever this is going to be 0, and 0 divided by, in this case it'd be negative 2, is still 0. But for others that may have not caught on, let me do this one more time for us. So 5 minus 5 squared times 5 plus 1 squared, and that's the numerator. Now we're going to divide that by 5 minus 7. So I know this is 0. Well, 0 times 49 is still going to be 0, and 0 divided by negative 2 is still going to be 0. So I know that the hole in the graph, there's going to be a hole in the graph at the coordinates 5, 1. So when x equals 5, there is, in fact, a removable discontinuity, because there is a y value. If there's a hole in the graph, we have to know where does it occur on the graph. Here's where it occurs. It occurs when x is 2, I gave this as just an example, and y is 1. Well, here, where does the hole occur for this particular function? It occurs when x is 5 and y is 1. We're going to do the exact same thing now for 7. So when I look at this, I don't actually have to plug it into my calculator. And I'll show you that I can, but here's the reason I don't have to plug it in. Because when I substituted 7 to try to find out what is the y coordinate, so I'm checking right now to see if there's a hole, right? And I'm checking at x equals 7. When I substitute 7 to the bottom, I end up with 0 in the denominator. Remember, we can never have 0 in the denominator. It's not possible, right? You're breaking a math rule. And that's why we say here that there's a vertical asymptote at x equals 7. There's a vertical asymptote at x equals 7. There's not a hole. There's not a hole. There's a vertical asymptote at x equals 7. Now, how can we do that on a calculator? So let me show you. Here we go. We're going to plug in 7. So we have 7 minus 5, quantity squared, and 7 plus 1, quantity squared. That's the numerator, and we're dividing by that by 7 minus 7. And you're going to see that it's going to say an error. It's going to say error because you can't divide by 0. And that's what tells me that instead of actually having a hole, we have a vertical asymptote. So we have a vertical asymptote at x equals 7. We have a hole at x equals 5 with the corresponding y value of 1. Jumping back up to, now that we have shown that we have a hole in the graph at 5, how can we express this in limit notation? And here's how we could express this. We could say, if I come off the side here where I have a little bit of space, we could say this limit, and we're talking about the function f of x. So this limit as x approaches the hole of 5 for the function f of x, as x approaches 5, so as it comes to 5 from the left and right, we are approaching a y value of 1. This would be the way to express this limit. So it doesn't mean that this actual ordered pair exists. This is where we're describing that it approaches this value. It doesn't mean that the actual ordered pair exists on that graph.